Hi everyone, welcome to this video series on the basics of university level physics. So this curriculum is going to follow the university physics textbooks, volume 1 and 2. So this chapter is part of volume 1, which is linked as shown on the screen. And if you're interested in downloading this note packet that I'm using, it will be provided in the description of this video. All right, let's get started. So 3.1 is just introducing terms we're using to describe different aspects of motion. So things like the location of an object, what direction the object is traveling, how fast it's traveling, how far it traveled. So we're going to go over all those and see some formulas for calculating them. Position is usually denoted as x, and it describes the location of an object relative to a frame of reference. So that's a lot of words, but location of an object seems pretty straightforward, right? It has to be relative to a frame of reference, which basically means you need some place to be like your x equals 0 starting point, and your measurement has to be relative to that starting point. So for example, we could have our frame of reference be the x-axis, or the frame of reference could be the Earth. Maybe you're measuring like a rocket's travel, and x would be like how high the rocket traveled. And so Earth would be your x equals 0. Or you could have x equals 0 as a dock that's facing the ocean, and your boat travels away from the dock in a straight line. And as it travels further and further, your position x gets greater and greater. Displacement is going to be the change in x. So this little triangle is the Greek letter delta, and it means change in. Conceptually, displacement represents how far an object traveled. In other words, if you have these 2 points where this is your starting point, x naught, and this is your final ending point, x final, you traveled this much, this arrow. And so displacement would equal change in x is the final position minus the initial position. And so for our example up here, we would use 4 minus 1 and say that our object has a displacement of 3 meters. And one more important thing to note is that displacement is a vector, which basically means it indicates both magnitude and direction. So just a quick overview of scalars versus vectors. Scalars are a number, so that would be like your position x, it's just a number. And then a vector would also be a number, but its negative or positive value tells you what direction it's indicating. So it's a number, but it also has some like plus minus value. So a negative displacement would mean the object traveled in a negative direction. Maybe that's like down, for example. And then a positive displacement would indicate that the object is traveling in a positive direction. So up, for example. So let's say we know how to calculate displacement. Now, how do you calculate the magnitude of the displacement? Maybe we don't care about the direction. That is going to be the absolute value of the displacement. So absolute value of change of x. And one more thing to note in physics notation is that each position xi has a time ti. So we put the little I there just as a placeholder for any numbers. So if we had a graph like this, where we had time on the x-axis and position on the y-axis, this is going to be very common. You will probably see this later on. Oops, I labeled those wrong. Then it's easier to see what I mean by xi and ti because we have maybe like t1 here and then t2 here and then maybe t3 here. 1, 2, 3 are just specific time points that we are interested in. Um, so they might have different x values corresponding to them. So maybe position 1 was here, position 2 was there, and then position 3 was here. And this just tells you how position is changing with time. It's similar to how I used x subscript f and x subscript naught up here to denote the final position and the initial position. Now for velocity. So velocity is the speed of your object's movement, also with direction. Average velocity is a vector that tells you how fast your object is moving. And so it has that magnitude, which is telling you how fast it's moving, but also it tells you direction. So positive velocity would be like speed in a positive direction, and then negative velocity would be speed going in a negative direction. And our formula for average velocity is going to be denoted with this x with a bar, v with a bar. That just means average. And it's going to be the final position minus initial position over the final time minus the initial time. You can also denote these as change of x over change in time. And our important note is that average velocity can be negative. So it can indicate that an object is moving in a negative direction. All right, let's do a quick example. I encourage you to pause the video and try this on your own. And then I'm going to go over the answers in 3, 2, 1. All right, so I'm going to assume that you read through the problem and maybe tried it a little bit. So we can see from this picture that Jill is kind of walking back and forth, and we're given all these informations. What I like to do when I'm approached with a lot of words is to underline the key information that is going to help me solve the questions. So I'm gonna look for all the numbers and then look at part A. So what is Jill's total displacement to the point where she stops to rest? Looks like they're asking what is the total displacement from this starting point, Jill's home, to this final ending point. So displacement requires us to look at all of the distances traveled, and the positives and negatives should cancel out. Jill first traveled 0.5 kilometers in a positive direction, then 0.5 kilometers back. So we subtract it, and then we add 1 kilometer because she went in the positive direction, and then we subtract 1.75 kilometers because she went in a negative direction. And in this case, she is going east for the positive or west for the negative. So east is that way and west is that way. All right, so let's finish our calculation. So these 0.5s cancel out, and then 1 minus 1.75 0.75 is negative 0.75 kilometers. So that is our total displacement. For part B, what is the magnitude of the final displacement? Magnitude is going to be the absolute value of the displacement. So we take the absolute value of negative 0.75, and we get positive 0.75 kilometers. Always remember to include the units in your answer because those are important and vary depending on the question. For part C, what is the average velocity during her trip? Let's see. Average velocity only requires you to know the starting point and the end point. So we're going to look for those. So the starting point seems to be position 0. So I'm going to say x naught is 0 kilometers. And our ending point, as we know from calculating total displacement in part A, is negative 0.75 kilometers. And what about the change in time? Because remember, average velocity's formula is change in position over change in time. So the change in time would just be the total time that passed during Jill's entire trip. So we can add together all of the minutes information we have. So I'm just going to do that down here. Change in time equals 9 plus 9 plus 15 plus 25. And the reason why I'm not doing like T final minus T naught is because when she started her journey, time was 0. So we add those together. That's 18 plus 40. So that's 58 minutes total. That's a lot of walking. And then we can plug all of our information into our average velocity formula. So the total change in position was negative 0.5 kilometers, and the change in time was 58 minutes. And you can use a calculator for this, but I'm just gonna box this as my answer since I'm a little lazy and I don't want to calculate it. For part D, what is the total distance traveled? So this is different from displacement. Displacement is your change in position relative to some starting point. But distance is asking about how far have you gone, regardless of a starting point. So we would add together all of the distances traveled. So we would get 0.5 plus 0.5, not negative this time. We're adding it because we're including it in the total distance traveled, plus 1 kilometer plus 1.75 kilometers. If it helps, you can think of it as taking the absolute values of each distance and not really caring about which direction it is. All that matters is there was some travel. And this is going to be 3.75 kilometers traveled in total. Now for part E, they want us to make a graph of position versus time. All right, so let's draw our axes. I'm going to try to do it as neatly as I can. And we're going to put time on the x-axis and position on the y-axis. For time, it's not very uniform. There's like 9 minutes and then 25 minutes. So I'm just gonna estimate where those would go on this axis that's separated by units of 10. And then for the position, I think it's helpful to draw the x equals 0 line somewhere in the middle of your graph because we're going into positive and negative positions. And I'm just gonna put this is -1, this is 1. All right. So I'm just gonna look back up at this picture for help. So in the first 9 minutes, Jill travels in the positive direction. So 0.5 and 9 minutes is about there. And then she goes back to her house in 9 minutes. So that's about there. So that's about at 18 minutes. And then she travels 1 kilometer in 15 minutes. So 18 plus 15 is about 32-ish. So we're gonna put a point there. And then 1.75 kilometers in the negative direction in 25 minutes. So 25 minutes is gonna be around here. All right. So hopefully this makes sense. We're basically just plotting the position with respect to t, and t is just the time passing. So here t was 9 minutes. Here another 9 minutes passed based on the question. So t was 18 minutes, and so on and so forth. And you can see if we think of this zero line as the house, Jill goes away from the house, back to the house, away from the house, and then past the house. So those graphs are very useful for interpreting the motion of an object. All right, we have one more example for checking your understanding. Again, pause the video and try this on your own. I'm gonna go over it in 3, 2, 1. So our cyclist rides 3 kilometers west and then turns around and rides 2 kilometers east. So since they don't give us a picture, I'm gonna draw my own. So let's say the cyclist starts, that's my bike. Hopefully that looks like one. So we're going west 3 kilometers. And then from there, we turn around and go 2 kilometers east. Now that we have a better understanding of what this looks like, let's start with part A. What is the displacement? So displacement is the change in x. So we go in the negative direction for 3 kilometers and then positive direction for 2 kilometers. So our displacement is going to be -1 kilometers because we're just interested in where did we end up relative to our starting point. So this was our starting point, and this is where we ended up. So what is that displacement? And we found it. Nice. Okay, for part B, what is the distance traveled? So remember, distance is not caring about the direction. We just want to know how far have you traveled. So distance is going to be 3 plus 2 kilometers, which gives us a total of 5 kilometers cycled. And then for part C, what is the magnitude of displacement? Again, magnitude is the absolute value of the displacement. So we take the absolute value of -1 kilometers and we get 1 kilometer. Just to emphasize the difference between displacement and magnitude of displacement. So displacement, it includes direction, but then magnitude of displacement, it does not include direction, it's just the magnitude. We're only interested in how big is that difference between our starting location and final location. Whereas displacement is interested in both how big is that displacement and in what direction was it relative to our starting point? So hopefully all this made sense. If you have any questions or suggestions, please leave them down in the comments, and I'll be back with 3.2 soon. Thanks for watching.